G'day, g'day.
Hello.
Good to see you.
Good to see you too.
We might get Ethan on at some stage soon, or maybe somebody else from the physics class. This is going to be this is going to be the video I'm going to put up for the problems. So when we did, sorry, give me a second. I'm still in geography. Okay, opening up the physics class. All right, so I posted the homework and the project. So there's chapter 17 homework, and there's capacitor fabrication.
Yeah.
I think I'm going to cover the capacitor fabrication first. So I'll just open this up and I'll talk about the rubric just for a second. Actually, wait a second. Share screen. And there. Okay. So capacitor fabrication, if you go into the physics school classroom, you should find capacitor fabrication. If you click on that, there should be a set of instructions here. And it should have a rubric as well. Okay, there we go. So that rubric has background, fabrication, testing, and presentation. So basically, what it is you must, so you're going to be writing about how capacitors work. The A level of that is you do it with the formulas. You create a capacitor, and the expert level of that is to actually have it in a functional circuit. And the testing of the capacitance, as in like prove that it is functioning as a capacitor. And the best level would be to do that without using a multimeter. So not the easiest things to do, but I do want to have some sort of differential there. The rubric there should be fairly self-explanatory on how to do it. I probably should attach a video as well on how capacitors work. I might even do that. I might even do that now. Edit.
My one question or maybe concern is gathering the materials for this project. I think I can get a multimeter, but I'm not sure about any sort of circuitry.
Circuitry shouldn't be that difficult to do. I mean, you're just attaching it into a circuit of some sort. So you have a battery, a capacitor, and maybe a diode and a switch. Or a light and a switch.
Yeah. When would this be due? It really depends on that, because we're stuck in quarantine until maybe next Monday, and then I can get out and maybe get supplies, but even then.
Yeah, okay. Maybe.
Because I'm excited. This project sounds really fun. When I was looking at it, I just want to be able to do it.
Okay. I was expecting to get through. I was expecting to get through chapter 17 by the end of next week, but that is looking less and less likely.
Okay.
We'll see. It may be end of next week. It may be the middle of the week after. I'm actually not sure. Capacitors explain. This guy has this guy. This guy. I think it's this video. Skip.
Hey there guys, Paul here from the Engineering Mindset.
Yeah, that's the one. This is the one. You can watch that later.
Capacitors, are those the things that help? Do they store the energy, or do they?
Yeah, they kind of like function. They function very similar to a battery, but if you think about it in terms of potential energy, you're not turning that electrical potential energy into a chemical potential energy and back into electrical potential energy. So it's actually getting rid of one of the steps.
Okay.
So one of the advantages of a capacitor is the rate at which it can discharge its energy. So batteries tend to have a sort of a trickle flow out. Like you're limited by how much of the chemical reaction can happen at once. Whereas
Yeah.
capacitors tend to discharge their charge really, really quickly. So if you have a capacitor that's big enough, like I'm not talking about farads or 100 farads, but like megafarad capacitors, that's what I think that's what they use at the moment in like the experiments for fusion, nuclear fusion, because
Wow.
yeah, so what they do is they build up this huge amount of charge and then release it in a millisecond, or fractions of a millisecond sort of thing, to be able to provide the energy to get the plasma going so they can try to get fusion working. A battery just wouldn't release the energy fast enough. Now, just to be clear, do not try to jumpstart a fusion reaction with this experiment that you're doing. Okay.
So, what are capacitors used for in everyday life?
So the video explains most of it, but if you have a capacitor, it's the most common is in use right here. So you have a thing called alternating current, where the current is changing, and you don't want it to be doing that. You don't want it going positive, negative, positive, negative, positive, negative.
Is that AC and DC?
Yes. So capacitors can make AC look like DC.
Okay, so basically you use capacitors for any sort of charging of any devices.
Yes, your phones, your computer power converters and all that. Most of that they will have a capacitor in there somewhere. Yeah.
All right, cool.
Okay. That would be a very difficult process to try to get that to work, but it would be the sort of thing that you'd want to get from if you were trying to get a mains power to work to get a device to work off mains power that required DC.
Yeah.
That's by the by. Okay. Moving on to questions. Unless you got more questions.
Nope.
Okay. All right. Moving on to the problems on page 489. So how do I've already edited that. Where's it's behind the little grid save. This Zoom thing, when you move the grid everywhere to be able to see the videos, it covers up stuff that you want to be able to want to click on. Okay. All right, so let's get back to, come on. Fine. Okay, so the chapter 17 homework is questions 1, 9, 14, 16, 31, 33, etc., etc. I'm going to focus on question 1 and 9 today. Just a note for people doing this, please don't do what you did in chapter 16 where the pages are sideways. It's very difficult to move the laptop on the side to read what you've written. So just a small request there. And these are the questions that I want answered, not anything else. So let's have a look at the first question here, question number 1, which is, how much work does the electric field do in moving negative 7.7 microcoulomb charge from ground to a point whose potential is 55 volts higher? Okay, so I'm going to stop sharing there, and I'm going to start sharing a whiteboard. Okay, so in very, very simple terms, you have this concept called electrical potential, which is different from electrical potential energy. So electrical potential energy is measured in joules.
And electric potential is measured in volts?
Yes. So the potential energy is measured in joules, but electrical potential is measured in volts. Now, volts
Yeah.
is equal to joules per coulomb.
Yeah.
Okay. This is basically.
And isn't it is E is electric field, right? But in this case, EP is electric potential.
In this question, we're not covering that yet. We're not covering that yet.
Okay.
So voltage is basically how many joules are that you need to apply to each unit of charge. So if you, it's difficult to think of it in terms of absolutes. So voltage is always a potential difference. So it'd be like saying the, do I have something here? So the potential energy of this book is different here as compared to here. But if we have to pick somewhere as it being a 0 point, and then after you've said this is 0, you then measure the difference in height. So voltage is the same way in that it's not necessarily measuring an absolute value, it's measuring the difference between 2 points.
It's relative.
It's a very relative thing. Okay, so let's do the first question here where you have a minus 7.7 microcoulomb, which is times 10 to the negative 6 coulombs. And we know that the potential difference is equal to, actually, can I get, yes, I can still use it. So the charge is equal to that, and your electrical potential difference is plus 55 volts. So it should be very easy.
And we're looking for,
you're looking for the amount of work done.
okay.
How much work does the electric field do in moving minus 7.7 microcoulomb charge from ground to a point whose potential is 55 volts higher? Okay, now the question here is this ground thing. Oh, you know, it doesn't matter because it says to a point whose potential is 55 volts higher. So it's from a grounded state to one that's 55 higher. It may or may not matter. No, I don't think it would.
So electric potential equals the charge multiplied by, what is it?
Well, my guess would be, if you look on page 471, equation 17 2a is voltage equals potential energy over Q. So that's
what it was.
And Q is the charge. So if I was to plug those into that particular equation, you would get 55. Let's rearrange that actually. We rearrange it because we're looking for the potential energy. So the potential energy would be equal to the voltage multiplied by the charge, or in this case, a quantity of charge. Remember to keep your signs.
Yeah.
So your potential energy should be equal to, I'm going to be very, very lazy and look up a calculator. 55 times 7.7, 423. So 420, it'd be negative 423 times 10 to the negative 6, which I will then make it a 10 to the negative 8. Wait. Is it become 10 to the negative 8? 4.2 times 10 to the negative 8 joules. Does that sound right? Yep. Okay, that sounds about right to me. So that's question number 1. Have a look at question number 9. It's a bit more.
Wait, you got to the power of -8?
Yes. It's teeny tiny.
I got something. I got the same numbers, but not to the power of -8.
Mm-hmm. So 55 times 7.7 gets you about, so it's roughly 8 times 5, 8 times 50, which is about 400. But that 400 is, you're just getting rid of the significant figures. I mean, I hope I've done that right.
Because it's using 7.7 nanocoulombs, which is microcoulombs.
Yes.
Which would be 7.7 times 10 to the power of -6.
Yes. That's your -6 here.
And I only get -4 then.
Oh, I'm going the wrong way. You're absolutely right. How do I edit this? Yes, I can edit. Yes, I can edit. Goodness, this program is fantastic. Okay, so it only goes to -4. Wow, that's a lot of joules for a it's a lot of joules for a small. So you can have something that has a lot of voltage and not much charge going through it.
Yeah.
Yep.
So then my question with this, I'm using an online, basically there's this website that helps with these problems.
Yep.
They give you kind of a step-by-step work through for some of them.
Yep. Hey, I'm not checking the stuff. You're quite welcome to go and have a look at how other people are doing it. Or were you going to be saying?
I have a question. It's just about the signs, keeping the signs.
Yes.
Because the way they do it, their answer is positive. I just don't know why. I don't understand that. I'm gonna mess up on that.
So, do you remember from your first semester work on vectors?
Yes.
So this is just telling you which direction it's traveling. It will be a positive amount, but it will be in the opposite direction. So if you did say that it was 4 times 10 to the -4 joules, that's fine.
Okay.
But it would just be traveling in the opposite direction in which the field is.
Yeah. All right, that makes more sense. So the signage is more. It's about direction.
It's about the vectors.
Okay.
Okay. Great. Let's move on. And we might get this done. So question number 9. 2 parallel plates connected to a 200-volt power supply are separated by an air gap. Okay, this air gap thing is actually very similar to what happens in a capacitor. How small can the gap be if the air is not to become conducting by exceeding its breakdown value of E equals 10 to the million, 3 million volts per meter? Okay, this is what happens with the Van de Graaff. If you get when the electric potential between your skin and the Van de Graaff reaches a certain amount, then you get a breakdown and the air actually becomes conductive.
Okay.
Okay, so
That's cool.
you
Yeah.
don't want that to happen. This is one of the reasons why when you make a capacitor, what you put in the middle is a dielectric. A dielectric is basically a non-conductive material.
Okay.
Okay. And I think we have Ethan Hargrave in there as well. Just let him in before we do this. G'day, Ethan.
Hello.
How's it going?
I'm alright.
Did you make it back okay?
Yeah, we're back in the States.
Okay. We're just going through some questions.
Alright, awesome.
Okay, so we're going to be doing two parallel plates here. Now, when you build up enough potential difference between the two of them, and the potential difference will change depending on how far away the plates are from each other, you will eventually get, actually I don't want to do this, you will get a spark between the two plates once they're close enough. So, very nice thing about plates is you get direct field lines. So your field lines are in one direction. Now, field lines are almost always, they are always. The field lines are always from the positive plate. So this will be your positive plate and this will be your negative plate. And this is just convention. I mean, Mr. Franklin had a 50-50 chance of getting this right when he was determining the type of electrical, what was the word that he was talking about? So he referred to this as an electrical fluid. He had a 50-50 chance of getting he determined that there were two types of electrical fluids in materials. We know it now as charge, but he was 50% right. He had a 50% chance of getting it right that the electrons, because I don't think he knew what an electron was at that stage, that electrons would be positive or negative. It would have been, in my opinion, it would have been easier if electrons were positive, but we've got them as negative, so that's where we go. Okay. What's the question? It's connected to a 200-volt power supply. So we now have an electrical circuit attached here. What color is that? So let's just keep it there. So you have a circuit coming off here to these two plates. And this is connected to some sort of power supply. Don't do that, silly machine. How do I draw a battery? I should have just had the square function. Okay, so which is the positive end of the battery? The positive end of the battery, the one with the little nub bit, or the one without? Can't believe I'm going to be looking this up. Positive end of the battery. Obviously, the bit that sticks out is going to be the positive end. All right. So if that's the case, what should happen here is that the positive end of the battery, if it's there, is that correct? Is that correct? I may have this wrong way around. Anyway, so the power supply here is 220 volts.
Yep.
Oh, 200 volts. And there is a certain amount of you have a limitation with air. Air, if you increase the voltage enough, if the potential difference is great enough, you will get a spark as the air becomes conductive. E equals 3 million volts per meter. Let's find where that reference is, so we can say where to look. Okay, typical voltages. Where do we have that breakdown?
So we do the electric field equals volt over distance, or the voltage over the distance. So the distance is the voltage over the electric field.
Yeah. The thing is, if you decrease or increase that distance, you can alter the voltage. If you maintain the power, so sorry, the voltage will remain constant because you connected it to a power supply. If you have two plates that are disconnected and you move them closer and further away, the process is completely different, because your voltage between the potential difference between these two plates can go around through this. Because it's connected to this power supply, the voltage on those two plates difference cannot change. As you change the distance between them, the voltage of these two plates, the potential difference, will not change. However, that would mean that if you had a 220 voltage difference here at, let's say, 1 meter, and it was disconnected, if you halve that, the two plates would not have a 220 volt difference, because you'd be inducing a charge on both of them. You'd be I think you'd be increasing the voltage by pushing them together, I think. Or is it reducing it? You might actually be reducing the voltage and increasing the charge. If you watch if you watch Walter Lewin's video, he explains how that works. We may have to figure that out before we can answer this, actually. Okay, so this is in reference to section 17.2. Section 17.2 has a bunch of equivalencies. So you have work where you can figure out the amount of, so if you remember that work is force over distance. If work is force over distance, and that's so that's a Newton meter. Work equals force divided by distance. And the unit for this is a joule. You can say that that's almost the same thing as energy. So by knowing this, you can get this into the formulas for potential difference by modifying the amount of distance that you have. If the force will be the same on every single piece of charge, or every single electron, because electrons are the ones that are going to be moving. Okay. Although they've written this as something completely different. Oh yeah, work equals. Oh, my bad. I am so sorry. Okay, so work equals FD. And this will also be equal to your charge multiplied by your electrical potential energy multiplied by your distance. Does that make sense? I'm seeing a bit of a I'm seeing an eyebrow raise from Aiden there. Okay, so your charge, which is this bit here, yeah, it's not selecting. So your charge is this bit here. You've got your volts equals joules per coulomb. So this is your charge. Oh, come on, just edit, you silly piece of, pardon me. Okay, so you have your charge here. This is what you'll be measuring in coulombs. Your I think the E is reference to what? What is E in reference to? Is that the electrical potential difference or the electrical potential or electrical potential energy? Is E electrical potential energy or electrical potential difference? I'm actually going to ask you guys for help here. It's either on page 473 or page 474. The effects of any charge distribution can be described either in terms of electric field or in terms of electric potential. Electric potential is often easier to use since it is a scalar, whereas electric field is a vector. There is an intimate connection between the potential and the field. Let us consider the case of a uniform electric field. That's the electric field between the two plates, such as between two parallel plates, whose difference of potential is VBA, so the point between point B and point A. The work done by the electric field to move a positive charge Q from A to B is equal to the negative of the charge in the potential energy, equation 17(2)B. So work equals negative charge multiplied by the voltage difference, voltage BA. We can also write the work done as the force times the distance, where the force on the charge is equal to the force on the charge is equal to QE. So it must be the electric field. Ah, okay. So that's the E is the strength of the electric field. So E is the strength of your electric field, which I don't think we're going to be doing much of at all. It's just there for the derivational purposes, I think. Please let that be the case. So if your charge in the electric field multiplied by the distance is the same as the work, you can have joules represented by this. Great. Okay, what do I do with that now? That's what they do. Okay, so then you take this. If you then have the work divided by Q equal to the electric field multiplied by the distance, you can then have the work divided by Q equal to the voltage. So the voltage is equal to the electric field multiplied by the distance between them. Okay. Huh. And because your voltage between the two equals ED, you can find your electric field as equal to, sorry, that's equal to the negative voltage of between the 2 points by the distance between the 2 points. And the unit for that is volts per meter. That makes sense. So that's your strength of your field. So that's what they give you. That's what they're giving you here. They're giving you this field. They're giving you the strength of this field here. This field, if it gets to 3 million volts for every meter, your air will then turn into a conductive plasma. I'm sorry that I muddled through that quite poorly. Did that make sense? Okay. Let's figure out what that was. That's when it will spark. Exactly. Exactly right. That's when it will spark. Okay. You know, I actually have to go through quite a bit of rigmarole to get to your chat things. It's easier if you put your voices on. Okay, never mind. We'll get this. So if I don't know the distance, and I know my E and I know my V, we just plug it into the equation. Very simple. Okay, so my E is 3 times 10 to the, where's my thing? 10 to the 6. And that's going to be equal to, is it minus 200?
Just 200.
I don't think it's going to make a huge difference, is it?
No.
Divided by the distance between them. So the distance between them we don't know. And with a bit of jujitsu, mathematical jujitsu, you should have 200 divided by 3 million. Yeah, the sign at the front actually doesn't matter because you only want the distance between the two plates. So you can get rid of that. So D equals 2/3 times 10 to the 4. to the minus 4. 10 to the minus 4 because you'll be dividing by 10,000. So that's a very, very small distance between them. This is actually one of the problems that they have when you make a capacitor, is if you get the plates too close together, they will not build up charge. So one of the things that they do is they find other substances to stick between them that have a higher than 3 million volts per meter. So if you put something like glass, or you put even something like paper will do a better job than air. That's why they are materials known as dielectrics. So the dielectric materials putting between the two plates will actually enable you to have the capacitor plates closer together without a discharge happening. Okay? And that covers questions 1 and 9. So you're one quarter of the way through the homework. If you haven't done the homework for chapter 16, I encourage you to get a handle on that, and I'm going to post this onto you guys who are back in Indonesia. So it's been a pleasure talking with you two tonight. I'm glad you got back to the States safely. Is there anything you want to say to your classmates here?
Hi guys.
Hi guys.
Well, thank you so much, Mr. Joe, for doing this, staying up late.
Yeah, thank you.
No worries. Maybe once a week I can do this. Okay.
All right. See you. Have a good
Adios.
night.
Thanks. Have a good night. Bye.
Bye.